Welcome to this exam review explainer. Listen, if you're a computer architecture student, there's a really good chance you're staring down a massive upcoming test. And let's be real, the topic of floating point addition, it usually looks like an absolute mess of ones, zeros, and shifting decimal points. I know it can feel incredibly overwhelming to try and track all those bits. But don't worry, we've got you. In this explainer, we're going to transform what seems like a totally chaotic process into a simple, foolproof masterclass. By the end of this, you're going to have a rock-solid, systematic way to tackle literally any floating point addition problem they throw at you.
Here's our game plan for today. We'll quickly cover the floating point foundation, break down a four-step algorithm, talk about aligning exponents, actually perform the binary addition, normalize the final result, and then wrap up with hardware logic and errors.
Okay, let's dive right into this. Section 1, the floating point foundation.
Before we even think about adding strings of binary together, we absolutely must have the basics down. If your foundation is solid, the math itself, it's going to be a breeze. So the very first concept you have to master is the bias. You see, in a standard format like a 32-bit float, the exponent isn't just stored as a regular negative or positive number. It's actually shifted. The system adds a constant value, the bias, which is typically 127, to make sure the stored exponent is always a positive binary sequence. So for your exam, you got to remember this. Extracting the true exponent is always the very first thing you do on your scratch paper. You take that stored number and you subtract the bias. You simply cannot do the math using the biased exponent. You must find the true value first.
Now, if you're still feeling a bit intimidated by binary, just think about good old standard scientific notation. Floating point numbers are effectively just a variation of that. In base 10 decimal, you already know that you can't just add 1.23 times 10 to the fourth to 1.23 times 10 to the second directly. No way, right? You have to match the exponents first. Well, binary is exactly the same, just with powers of 2 instead of powers of 10. So if you have 2 to the 6th and 2 to the 3rd, you have to adjust one of them so the exponents match up perfectly. Honestly, if you can do it in decimal, you can absolutely do it in binary.
Moving on to Section 2, the four-step algorithm. To avoid getting completely lost in the weeds during a stressful exam, I want you to memorize this four-step flowchart. It's your unbreakable sequence, your ultimate algorithmic cheat sheet. Step 1, extract your numbers from the floating point format into scientific notation and unbias that exponent. Step 2, align the exponents so they match. Step 3, add the mantisses together using standard binary addition. And Step 4, normalize your final result and repack it into the required format. Trust me on this, if you follow these 4 steps in order, you simply cannot fail the question.
Next up, Section 3, aligning the exponents.
Let's zero in on Step 2 of our algorithm. I'll be totally honest with you here, aligning the exponents is a tricky spatial challenge, and it is exactly where most students make their fatal mistakes. You're shifting all these bits around, and it's so incredibly easy to lose track of where your radix point, which is basically the binary decimal point, actually is. But there is an absolute rule you must burn into your memory. When you're adjusting an exponent to match another, you have to compensate by moving the radix point in the mantissa. If you drop an exponent down, say from 2 to the 6th down to 2 to the 3rd, you're decreasing the exponent. So you must move the radix point to the right. And on the flip side, if you increase an exponent to match a higher one, you move the radix point to the left.
Please, whatever you do, do not try to hold these bit shifts in your head. It's a trap. Instead, set your scratch paper up with a standardized column-based table. Just lock your radix point into a fixed, unmoving column. For instance, if we're trying to add a number with an exponent of 2 to the 3rd to a number with a 2 to the 1st exponent, we might decide to increase the 2 to the 1st up to 2 to the 3rd so they match perfectly. Because we increase the exponent by 2, we must shift our bits 2 places to the right relative to that fixed radix point. By using distinct columns for halves, quarters, eighths, and so on, your radix point stays perfectly anchored and the bits just naturally slide into their new homes.
But here's a crucial warning. When you slide those bits over, you're going to create empty gaps, always. Always backfill those empty columns on the right side of the mantissa with zeros. If you leave them blank, in the heat and panic of an exam, your eyes are going to play tricks on you. You'll accidentally slide a bit into the wrong column during the addition step, and your entire answer will be completely wrong. Just pad it with zeros to lock those columns firmly in place.
Which brings us nicely to Section 4, performing the binary addition.
Now that your setup is absolutely flawless and perfectly aligned, we hit Step 3. And honestly, this is the easiest part.
Because we aligned our radix point and padded everything with zeros, we're just doing standard binary math straight down the columns. Look at this. 0 plus 0 is 0. 0 plus 1 is 1. 0 plus 1 is 1. 1 plus 0 is 1. The radix point stays exactly where it is. 1 plus 0 is 1. If we had a column where 1 plus 1 occurred, we'd simply write 0 and carry the 1 over to the next left column, literally just like grade school addition. Careful preparation makes the actual math incredibly straightforward.
Okay, nearly done. Section 5. Normalizing the final result.
So, the crucial point here is, when you finish that addition step, you are not done. Handing in a raw sum will lose you major points on the test. Floating point fields require a very strict formatting standard. The core normalization goal for these standard formats is to adjust the result so that there's exactly one single one to the left of the radix point. That raw sum you just got, it might have multiple numbers to the left of the point, or it might have a 0 to the left and a bunch of zeros right after it. That needs fixing.
Let's say our raw sum came out to 01110 with an exponent of 2 to the third, while that leading 0 isn't normalized. To get exactly 1 sitting to the left of the radix point, we have to shift our point. And notice this. Every single time we shift the radix point to the left to capture that 1, the exponent has to step up to compensate. It climbs from 2 to the third, up to 2 to the fourth, and then to 2 to the fifth. You track this movement carefully until that format is absolutely perfect.
Once your binary number is fully normalized, you execute step 4, repacking. First, you determine your final sign bit, 0 if it's positive, 1 if it's negative. Then you take that final exponent we just bumped up, and you must rebias it by adding that constant, like 127, back into it so it's ready for storage. Finally, you take only the mantissa bits that sit after the radix point and slot them right into the final constant field. Remember, for standard normalized floats, that 1 to the left of the point is implied, so you don't even need to store it.
Finally, Section 6, Hardware, Logic, and Errors.
To wrap up our explainer, let's step back and look at the big picture. You've just learned how to do this manually on paper, but there is a massive difference between human calculation and hardware logic. A CPU isn't pulling numbers out into scientific notation like we just did. It uses really complex floating point adder circuitry, temporarily storing 25 or more bits of precision during those shifts to ensure total accuracy. The hardware flawlessly handles all these crazy, complex, denormalized corner cases at lightning speed. But for us humans, running on caffeine and using a number 2 pencil, extracting the values manually into our scratch paper columns is infinitely safer. Trying to mimic the hardware in your head is just a guaranteed way to mess up.
And that actually leads us to a guaranteed exam question topic, precision loss. You see, computer architecture has real physical limitations. If you have an 8-bit mantissa, you literally only have 8 physical slots in the hardware. So if adjusting your exponent requires you to shift your mantissa way over to the right, some of your bits, maybe the ones representing tiny fractions like quarters or eighths, are going to be pushed completely past the fixed mantissa limit. When they fall off the edge, they are dropped forever. This introduces immediate rounding and precision loss.
So, I want to leave you with this thought as you hit the books. It's a question software engineers grapple with all the time. If your system has limited mantissa space, which bits are you willing to just lose? When you shift an exponent massively, you're making a hard choice to sacrifice accuracy at the smallest fractions just to accommodate the larger whole numbers. Understanding this physical trade-off isn't just about acing a test. It's about understanding the very boundaries of computer science. Master these 4 steps, draw out your columns, pad your zeros, and you are absolutely going to crush this exam. Good luck.